This is video 34 of Tensor Calculus. In this video, we're going to introduce the product rule as it relates to the covariant derivative. For the last 6 videos, we've been exploring the covariant derivative. We now know how to find the covariant derivative of an individual vector component using one of the two expressions you see here. Well, now we want to begin to look at some more complex expressions. In particular, we want to look at this one, SI T J. Now, this is, of course, a tensor product, and we want to know what it's like to take the covariant derivative of such an expression. Well, let's start by reminding ourselves of how this works for simple partial derivatives. If we were to take the partial derivative of this expression with respect to zk, we'd simply use the product rule. We'd find the partial of SI with respect to zk and multiply by tj. Then we'd use SI times the partial derivative of tj with respect to zk. This is simply the product rule, something you learned in first year calculus. Well, we've said many times that the covariant derivative is really just an extension of partial derivatives to make it more general so that it works with curvilinear coordinates. So it's quite reasonable to expect that the same sort of pattern would work for the covariant derivative. So let's look at what that might look like. The covariant derivative of SITJ, if we were going to apply a product rule to this, it would be the covariant derivative with respect to k of SI times TJ plus SI times the covariant derivative of TJ. All right, so the question is, does this make any sense? Well, there are two guiding principles we look for in seeing if we have a valid expression for the covariant derivative. The first is we're going to insist that the result always be a tensor. And that's the whole point of a covariant derivative, is to know that whenever we find the covariant derivative, we will be producing a tensor. So let's look at that first. Well, here we have a covariant derivative of a vector component, and we know that produces a tensor. Then we multiply that by a vector component, which is a tensor, so the product of two tensors is a tensor. And we have the same argument over here. This is a tensor, and when we multiply by SI, then the product is a tensor, and of course the sum of the two is a tensor. So yes, this expression does produce a tensor. Now the second guiding principle is that when we apply the covariant derivative to affine coordinates, we expect that the expression will reduce to the correct expression using simple partial derivatives. And let's see if that works. In affine coordinates, this expression is just going to be this. And this expression is just going to be this. In other words, our expression here reduces to this one if we're dealing with affine coordinates. So this pattern that we've written down here does in fact meet both criteria. It's a valid tensor, and it produces the correct results in affine coordinates. So now let's expand this out and see what it looks like in more detail. So the covariant derivative with respect to k of SI TJ is going to be this. First of all, instead of this symbol, we'll expand this out using our expression for the covariant derivative of a covariant vector component. So here we're going to have the partial derivative of SI with respect to zk minus the Christoffel symbol of, let's see, we're going to have ki here, and then we're going to form a contraction with s, I guess we'll use the letter m here. So this expression is the covariant derivative of SI. Then we'll multiply that by TJ plus SI. And now we'll expand this second term using our first expression. So we're going to have the partial derivative of Tj with respect to Zk. And we're going to need a plus sign this time for our Christoffel symbol. And the indexes are going to be J, K, and we'll use M again with T, M, like so. All right, now let's expand out the terms. We'll multiply Tj by both of these factors and Si by both of those factors. All right, now if you look closely, you'll see that this term plus this term is the same as this term plus this term. And that means that these two taken together is equal to this. Thus we can write our final expression like this. Now, let's take a minute to compare this result with the individual expressions we have up here. Now, there's some similarities here. We're taking the covariant derivative, of course, and the first thing we do in each of these is to find the partial derivative. Well, the same thing happens here. We take the partial derivative of the original expression unaltered. Now here we add a term with a contraction using the factor that we're dealing with here. And here we have a different term with a contraction this way involving this term. Well, in our new expression, we have two factors. So we have two terms here, one that deals with a contraction of S and the other that deals with a contraction of T, like so. So it's a combination, if you will, of both this expression and this expression. Because we have two factors, we have to have two separate terms added on, one to represent the contraction of each of the two factors, like this. Now, it doesn't take a great deal of imagination to understand how this principle generalizes. Let's imagine that we have yet another term here. Let's say Q, with some index right here. What effect would that have? Well, if we had three factors here, we're going to wind up with a third term because our product rule means that we're going to take the derivative of each factor one at a time, leaving the others fixed as we go. Well, the same thing happens here, and that means the same thing's going to happen here. And ultimately, that's going to result in an additional term out here. In other words, the generalization here is that when we have a product of factors like this, we're going to first take the partial derivative of the entire expression. Then we're going to have a term that looks like this for each of the factors within our expression. And each term, the form of it is going to be governed by whether the index is a lower index or an upper index. If it's a lower index, we're going to have a negative term, and the contraction is going to be formed from high to low. If it's an upper index, it'll be positive, and the contraction will be formed from low to high. So that pattern can be extended as far out as we need to. It works for as many factors in our product rule as we might encounter. Now I'm going to do another example in just a minute, but before I do, I want to do something else. What I want to do is to see what happens if our tensor product is actually a contraction. That is, instead of SITJ, it's SITI. So let's take the covariant derivative of this with the same pattern that we used just above here. So we're going to get something that looks almost identical. We're going to take the partial derivative with respect to ZK, k of our product, Si, Ti. Then we're going to have these two terms, but we're going to have gamma m ki sm. This time it's Ti instead of Tj. And the last term is gamma I this time, Km Si Tm. Alright, now it looks virtually identical, but the major difference is instead of having ij here and here, we've got another dummy index. We've got a contraction going on this way as well as the contraction with the m's this way. Now over here we've got the normal contraction of the factor like this, but we also have another dummy index going in this direction. So look what happens when we rename index I to m and index m to I. And when we do that, you'll notice that this term is identical to this term, except one's negative, the other's positive. That means they're equal and opposite, so they cancel each other out like this. And that means that our final expression looks just like this. It's the covariant derivative of Si Ti is simply the partial derivative with respect to Zk of our contraction Si Ti. Now, you know by now that a full contraction like this, Si Ti, is actually a scalar function. And so we ask the question, does this still make sense? Could this possibly be true? Well, yes, we learned back in video 27 that the partial derivative of a scalar function is just a covariant tensor component, which of course is a tensor. So that means that this expression still produces a tensor, and it does so regardless of what coordinate system we might be using. So we can generalize it this way. The covariant derivative of a scalar function is going to be equal simply to the partial of that scalar function with respect to our index here. So this is a statement that is true for all coordinate systems. The covariant derivative of a scalar function is just the partial derivative of that scalar function. All right, so now let's wind things down with another example. Now at first glance, a problem like this can look quite intimidating, but as you're going to see, it's not nearly as bad as it first looks. The first thing we always do is to take the partial derivative of our expression. So we'll take the partial derivative with respect to ZR. R is the index we're using for the covariant derivative, and that's going to apply to the entire expression unaltered. So it's just going to be the partial derivative of AI, Bj, Ck, Di, and Em like this. All right, now we're going to need a term with the Christoffel symbol in it for each of the indexes. However, if you look closely, we have a dummy index here, I and D. And anytime we have a dummy index, we can ignore these indexes because the term we get for this guy and this one are going to cancel each other out just like it did on our previous analysis. So we can simply ignore these two. Thus, I need extra terms for B, C, and M only. All right, so here we go. We're going to need, first of all, a term for Bj. So it's an upper index, therefore we're going to need a positive term, and it'll be gamma, and it will have, I'll put the indexes in later. This is often easier to do this way. Write down all of the factors first, and come back and fill in the indexes. All right, so we're forming a contraction using index J here. So we're going to have S as a dummy index on B like this. Now, we always place the index that we're using for the covariant derivative as the first index in the lower position right here. So if we're going to form this contraction, then the S index fits right in here like this. The next thing is that since we bumped J out of the expression, J goes back to this position. And now all the other indexes just fill in as they are originally located. So this is CK, DI, and EM. So we've formed a contraction using the B factor right here. All right, we move on next to CK. This time it's a lower index, so it's a negative term. It's gamma. All right, we'll fill in the letters A, B, C, D, and E. And R is always this guy right here. And then we're going to form the contraction with C. So this is our contraction, our dummy index, and that has to match up here. And then the guy that we bumped, which is K, is going to fill this slot right there. And then we fill in everything else as is. AI, BJ, DI, and EM. And finally, we can skip over DI because it's part of a contraction here. So the last factor is with M. It's a lower index, so it's going to be a negative term, gamma, A, B, C, D, E. Again, this is R. So now we're forming a contraction with E, so this is our dummy index combination. And since we bumped M out of the way, then M fits right here, and everything else fills in as it was originally. And that's our final result. So as you can see, with a little practice, these kinds of expressions almost write themselves. Okay, I think that's going to be enough for this video. Let's go do a recap. The first thing we did was to realize that a covariant derivative of a product of factors like this can be dealt with exactly the same way we deal with it with partial derivatives. We use the product rule. And the product rule is this. We find the covariant derivative of the first factor and multiply by the second factor. Then we use the first factor and multiply by the covariant derivative of the second factor like this. That's the exact same structure that we use for partial derivatives. We then went on to expand the expression and realized that we can represent it like this, that the covariant derivative is going to be equal, first of all, to the partial derivative of the entire expression, followed by a series of terms. And there will be one term for each of the factors in the expression. And the factors are either going to be negative or positive, depending on whether the index is in the lower position or the upper position. And that's also going to dictate whether the contraction goes from high to low or from low to high like this. Now we also pointed out that this is expandable as well. If we had a third term here, if there were three terms, then on the right side we're going to have an additional term here. And that in turn is going to result in an additional term here. So we can generalize the process realizing that we first take the partial derivative, then we have a term like this that corresponds to each of the factors in our expression. We then went on to look at what happens if our tensor product is actually a contraction. We realized that it's a scalar function, and when we apply this pattern, we find that these two terms cancel out, leaving us with just with the partial derivative. And that led us to understand that the covariant derivative of a scalar function is just the partial derivative of that scalar function. And that's true for all coordinate systems. In a sense, it follows the same pattern up here, because what we're doing is taking, first of all, the partial derivative, and then we're adding a term for every index. Well, there are no indexes here, so there are no terms. So the same pattern holds true for a scalar function. And then finally we worked a more complex example here. And this illustrates all of the points. First of all, we start by taking the partial derivative of the entire expression, and then we walk through each of the free or live indexes, forming a contraction. So we only need to deal with B, C, and E. So here we have a contraction formed with B. Here we have a contraction formed with C. And here we have a contraction formed with E. And so just by walking through each of the free indexes, we can write these terms down just by inspection. With a little bit of practice, I'm sure you'll be able to pick up on this in no time. Now, everything we've done with the covariant derivative so far has involved vector components, or tensors of rank 1. In the next video, we're going to look at what it means to take the covariant derivative of higher rank tensors.